Okay, in this video, I'm going to do a quick recap of how to solve linear systems using the substitution method. The basic idea here, again, I'm solving a linear system, so I'm finding the point of intersection between these two lines. But I'm going to do it this time without graphing the lines, which is an important skill because graphing lines is not going to give us a precise answer, especially if we're dealing with fractions or large numbers or things that we're unable to graph accurately. Or maybe we just don't like to use graph paper, we don't have any graph paper. So we're going to learn here an algebraic method. We're going to start the exact same way. I'm always going to label my two equations, equation 1 and equation 2. And what we want to do is, I don't know how to solve two equations with two variables or two unknowns. We don't know how to solve that. I want to turn this situation into just one equation with one unknown. And I'm going to do that through a process called substitution. So I know that in equation 1, x equals 2y plus 3. So that means x is always equal to 2y plus 3. So I can replace x in the second equation with that expression 2y plus 3. So what I'm going to write is that I'm going to substitute 1 into 2. So I'm going to replace x in equation 2 with that expression that we know x is equal to 2y plus 3. I'll just do it in another color just to show you how this works. We're always, again, substituting with brackets. So I've replaced x with 2y plus 3, and everything else in the equation is going to stay the exact same. So I've got plus 3y equals 13. And you might notice now that I have one equation and one unknown. So check after substitution step. I've done it well here because I've got one equation and one unknown, and we know how to solve that. So I'm going to distribute to get rid of the bracket. So 2 times 2y is 4y. 2 times positive 3 is positive 6. I'm going to collect like terms. So 4y plus 3y, I've got 7y plus 6 equals 13. I want to get y by itself, so 6 comes to the other side. 13 minus 6 is 7. So I have 7y equals 7. So y equals 1. Great, so I've solved for 1. I've solved for y. That doesn't mean I've solved the problem. We're only halfway. When I'm solving a system, I need an x and a y because I'm trying to find the coordinates of that point of intersection. So what I can do is I can sub y equals 1 back into either of my two original equations. Either one will work. You can pick what's ever easier. It looks to me like equation 1 is going to be a little bit more straightforward because I've already got x equals on the left side. So I'm going to sub y equals 1 into 1. I always want you to annotate or kind of explain each part of the procedure. So I'm now going to rewrite equation 1, but instead of y, I can now plug in the number. I know that y is equal to 1. So x must equal 2 times 1 is 2 plus 3, so x equals 5. So now I can write my therefore statement. So I always remember a solution to a linear system is always a point of intersection. So the POI is 5, 1. And again, if I want to verify that I'm correct, I need to do two left side, right side checks. For equation 1, I can do a left side, right side check. I want to verify that this point is on that line. So I'm going to take the original equation 1. The left side was just equal to x. The right side was equal to 2y plus 3. So I'm going to physically separate them. I'm going to plug in, well, I think x was equal to 5. And on the right side, I think y was equal to 1. 2 times 1 is 2, plus 3 is 5. So, okay, so we know the point 5, 1 is on the first line. Is it also on the second line? I need to always do a second left side, right side check because our POI is that one point that's on both lines. So my original equation 2 on the left side had 2x plus 3y. And on my right side, I just had 13. So I'm always using my original equations. I think x is equal to 5. And I think y is equal to 1. 2 times 5 is 10. 3 times 1 is 3. So now I've verified my solution because my left side is equal to the right side. So this point is the only point that's on both of these lines. So that's how I can solve a system of linear equations without graphing. We're going to just do one more example, or at least start one more example. So I've got equation 1 and equation 2. Here, it's a little bit harder to see which of the variables I can isolate. So before I substitute, I need to have x or y by itself on one of the sides. And I can isolate either x or y in either equation 1 or 2. So what's probably the easiest? Well, I've got 2x, I've got a negative 3y, I've got a 3x. This y is by itself. That's going to be the easiest. So I'm going to rearrange equation 2 to isolate y. So I can pick which variable is the easiest to isolate. I want to kind of avoid fractions, avoid doing too much algebra. So I'm just going to move that positive 3x to the other side. So I now have 8 take away 3x. Why don't we call this equation 3? Now I've got y isolated. I know this is equal to y. So I can substitute this expression for y in for y in equation 1. We always have to substitute it back into the other equation. Otherwise, we're just going to go in a loop and we're not going to learn anything new. So I'm going to sub my rearranged equation 3 into 1. So this time, because I've isolated for y, I'm going to copy the equation the exact same, but I'm going to replace y with what I know y is equal to, 8 subtract 3x. And again, you notice here I've got one equation with one variable, and that's what I've learned how to solve in grade 9 or in the first week of grade 10 math. I'm going to distribute. Negative 3 times 8 is negative 24. Negative 3 times negative 3x is positive 9x. Be careful with the signs. Remember, negative 3 times negative is going to be a positive. And again, I can collect. So I've got 2x plus 9x. So I've got 11x minus 24. I want to get x by itself. I'm going to move the negative 24 to the other side. So I'm going to add 24 to 20. So I've got 44 equal 11x. And I divide by 11. So x is equal to 4. Again, I'm only halfway because I need an x and a y to get my POI. So I'm going to sub that in. So I'm going to sub x equal 4 into whatever equation you prefer, right? The point is on both lines. Let's put it into 2. You can pick whatever looks easier for you. I like to avoid fractions. I like to have positive numbers. Whatever looks easier. So I'm going to replace x with what we think x is, what we know x is, which is 4. Then I'm going to solve for my other variable, which is y. So I've got 3 times 4 is 12, plus y equals 8. So I'm going to move 12 to the other side. So I'm going to take away, I'm going to do 8 minus 12. So y is equal to negative 4. So I always need a solution for x and y, which I can then summarize in my POI statement. So the point of intersection, which is a solution to the linear system, in this case is 4, negative 4. So again, whenever we're solving by substitution, I need to isolate one of the variables in one of the equation and then substitute that equation into the other. And what that does, why we're doing this, is because I'm turning two equations with two unknowns, which we can't solve, into just one equation with one unknown, which by now we should be pretty comfortable with solving. And again, if you wanted to, you could verify with the left side, right side check. I'm not going to do that in this video. But again, if you have any questions, please send me an email or ask in our Google Meet. And thanks for watching.